Okay, this show's topic even has Bigfoot shaking his head in disbelief. The quantum computer race is getting serious as artificial intelligence speeds up breakthroughs. This will probably leave you shaking your head too. Here we go. We're taking a deep dive today into the truly head-spinning developments in quantum computing.
It really is moving fast.
Yeah, recent progress from, well, both China and Microsoft, and it seems like AI is just pouring fuel on the fire, speeding things up.
Absolutely. It's accelerating the research itself.
So our mission today is to try and unpack two key breakthroughs: China's Zuchongzi 3.0 quantum chip and Microsoft's pretty innovative Majorana 1 quantum AI chip.
Two very different approaches, too, which is interesting.
Right, and why should people care? I mean, this isn't just tech giants one-upping each other. It's...
No, not at all. These leaps, they could genuinely reshape whole industries. Maybe even, change how we understand reality itself. It's fundamental stuff.
Okay, so the pace is just striking. It felt like sci-fi not long ago.
Exactly. Theoretical physics, mostly. Now we're seeing actual hardware with capabilities that honestly were hard to imagine just a few years back.
And these strategies from China and Microsoft, they're quite distinct paths to try and crack this quantum nut.
Right. Very much so. They're tackling the huge challenges of building practical quantum computers from, well, different angles.
All right, let's focus first on China then. The Zuchongzi 3.0 processor, the specs alone, they make you sit up.
They do. It's a 105-qubit design.
105 qubits. And maybe even more important, the fidelity rates. They sound incredibly high.
That's really key. 99.90% for single qubit operations,
Okay.
99.62% for two qubit operations, and 99.18% for readout. That level of precision is, well, remarkable at this stage.
So what does that high fidelity actually mean in practice? Like, what does it buy you in terms of raw power?
It means fewer errors. Significantly fewer errors. Quantum computations are notoriously prone to noise and errors, so higher fidelity means you can run much more complex calculations reliably. And the power they demonstrated, it's pretty staggering. The Chinese team showed it solving a specific, very complex problem in just hundreds of seconds.
Hundreds of seconds. And how does that stack up against, say, a regular supercomputer?
Well, they compared it to Frontier, which is currently the world's fastest supercomputer.
Okay.
Frontier would reportedly need an estimated 6.4 billion years to solve that same problem.
6.4 billion years compared to a few hundred seconds.
Yeah, the scale of that speed up is almost, well, can't really wrap your head around it.
That is mind-boggling. So the Chinese team calls this quantum computational advantage. How's that different from quantum supremacy, which Google talked about a few years back?
That's a good distinction to make. Quantum computational advantage, as they're using it, really emphasizes the practical side. It's about showing their machine can beat classical supercomputers on specific, complex tasks that could actually have real-world value.
Oh, okay. More applied.
Exactly. Whereas quantum supremacy, the term Google used with their 53-qubit Sycamore back in 2019, was more about proving the principle. Showing a quantum computer could do something, anything really, that was beyond classical reach, even if the task itself was a bit, contrived.
Right, like a benchmark test.
Sort of. Sycamore solved this problem in 200 seconds versus maybe 10,000 years classically. Zuchongzi 3.0 tackles a much harder problem and shows an even bigger gap compared to today's best classical machines. It moves the goalposts significantly.
So we're moving beyond just demonstrations. Zuchongzi 3.0 is showing muscle in areas that could actually matter. What kind of problems are we talking about? Which industries might feel this?
Well, the combination of speed and that high precision opens up possibilities for really tough problems. Cryptography is a big one.
Breaking encryption.
That's the concern, yes. It definitely puts pressure on current encryption standards. But also optimization problems. Think global logistics, shipping routes, financial modeling, risk assessment, and large-scale simulations. This is huge for things like material science, designing new materials from the atom up, or drug discovery, simulating how molecules interact, even complex supply chain optimization.
Wow. Simulating a new drug or a whole logistics network, the detail you could achieve.
Exactly. A level of detail we just can't manage today with classical computers. It could revolutionize scientific discovery and industrial efficiency.
And China's achievement here, it's not happening in a vacuum, is it? This is clearly part of a global race.
Oh, absolutely. It's a direct challenge to other big players.
Yeah.
Google, for instance, recently announced their own 105-qubit processor, Willow.
Same qubit count.
Same nominal count, yes. But the performance metrics of Zuchongzi 3.0 is reporting suggest they might have an edge right now in terms of practical application power.
So it's more than just tech bragging rights.
Much more. It's geopolitical, it's economic, it has huge implications for national security, for the future of AI, for fundamental research. Leading in quantum could give a nation a massive advantage across the board.
And it seems clear China is investing heavily, state-backed investment. Zuchongzi 3.0 isn't their only project.
No, definitely not. They have a clear strategic goal, backed by serious government funding, to be a world leader here. They're also working on things like the Zhujiang photonic quantum computer.
Photonic, using light.
Yes, a different approach. And the TAN 5004 system, they're pursuing multiple paths, showing a real commitment. But of course, the U.S. is heavily invested too, with Google, IBM, Microsoft, Rigetti, plus Europe, Canada, Australia. It's a global effort. And that competition is driving progress.
Okay, let's pivot then. Let's talk about Microsoft's Majorana 1, the quantum AI chip. There was some really wild stuff reported initially, even talk of accessing parallel realities.
Yeah, that definitely caused a stir. It got a lot of headlines.
So what's the core idea behind this chip? How is it different from the superconducting qubits in Zuchongzi?
It's a fundamentally different path. Microsoft isn't using those standard superconducting qubits, which can be quite sensitive to noise. They're focused on developing what's called a topological qubit,
Topological qubit.
based on a theoretical particle called the Majorana fermion.
Okay, refresh my memory. Classical bits are 0 or 1. Qubits can be both at once, right? Superposition.
Exactly. That's the core quantum advantage. Remember the maze analogy. Classical goes down one path. Quantum explores many paths simultaneously. Microsoft's approach with Majorana 1 aims to harness this, especially for complex simulations, say in chemistry or material science.
Simulating molecules,
Sure.
drug design, new materials.
Right. Understanding things at the electron level, maybe even designing self-healing materials eventually.
And this Majorana fermion idea, it's been around a while, hasn't it? Microsoft's been working on this for some time.
A long time. Their research goes back to around 2004, nearly 2 decades. The particle itself was theorized way back in 1937.
Wow.
For years, the challenge was figuring out how to even detect it, let alone use it. The big breakthrough involved discovering a new state of matter, a topological phase.
Beyond solid, liquid, gas.
Right. And that discovery allowed them to create what they call a topological superconductor.
Topological superconductor. Sounds intense. What's the advantage? Why topology?
Stability. That's the main claimed advantage. Topological qubits are theoretically much more resistant to errors. See, regular qubits are fragile. Tiny disturbances, noise, heat can make them lose their quantum state decoherence.
Right, the error problem.
But topological qubits, their quantum information is kind of encoded in the overall structure, the topology. It's inherently protected, making them much more robust against that environmental noise.
So built-in error resistance.
That's the goal. And if it works as hoped, it could lead to smaller, more scalable quantum computers, potentially without needing the extreme cooling and isolation some other systems require.
That sounds like a huge deal for actually building usable machines. How do they actually make the Majorana 1 chip then? How does it use these particles?
Well, they use this special new material, the top conductor, arranging atoms with incredible precision. This specific arrangement creates that topological phase where the Majorana fermions can exist and be manipulated. So the quantum information is encoded using these Majoranas protected by the topology. And because of this approach, the qubits themselves are tiny, like 1/1100th of a millimeter.
Whoa. So they could potentially fit a lot on one chip.
Millions, potentially. That's the scaling argument.
So while others are maybe racing for just more and more qubits, Microsoft's strategy is different. Focus on making the qubits better, more error-resistant, and scalable from the start.
Precisely. It's not just about the raw count right now for them. It's about building a foundation that's inherently stable and scalable. They believe this built-in error resilience will ultimately allow for much larger, more reliable systems with less need for complex external error correction.
Which is a massive overhead for other systems.
It is. And another interesting point. This approach might allow quantum processors to eventually be integrated into existing data centers.
Really? Not needing a whole separate, crazy facility.
That's the potential long-term vision, unlike some other quantum proposals. It makes the integration path seem potentially a bit smoother.
That is compelling. So what applications could this kind of robust, scalable quantum computer unlock?
Well, again, chemistry and material science are huge targets. Simulating molecules accurately could revolutionize drug discovery. Designing catalysts for cleaner energy, new battery technologies,
Better batteries, yes, please.
climate modeling with far greater accuracy. And then there's the synergy with AI we touched on earlier.
Right, quantum feeding AI.
Exactly. Quantum computers could run simulations generating incredibly rich data sets far beyond what classical computers can produce, which AI models could then learn from. Think better weather forecasts, smarter supply chains, designing personalized medicines based on your genes.
It's like quantum provides the super-powered input for AI's analysis.
A really powerful combination, yeah. Quantum handles the incredibly complex simulation part. AI finds the patterns and makes predictions.
Okay, so Zuchongzi 3.0, Majorana 1, huge steps. But we're not quite there yet, are we? What are the big hurdles still remaining?
No, definitely not plug and play yet. Quantum error correction remains a massive challenge.
Even for the topological ones.
Well, Midjourney 1 aims to tackle it inherently, but proving that at scale and achieving true fault tolerance, where errors are essentially negligible, is still a huge research effort for everyone. The Zuchongzi team, Google, everyone is working hard on error correction techniques too.
And just scaling up reliably.
Scalability is the other big one, making these systems bigger while maintaining control and coherence. Microsoft's tiny topological qubits offer a potential path, aiming for millions on a chip, but demonstrating that is the next step.
And of course, all these claims need checking, right? Peer review and independent validation.
Absolutely critical,
Mm.
especially in a field moving this fast. Rigorous peer review, independent verification that's essential to confirm these breakthroughs and ensure they're reproducible before we can really build upon them. Science needs that scrutiny.
Makes sense. Looking bigger picture, what are the sort of strategic implications if one country or company really pulls ahead here?
It could be enormous. Think about the impact semiconductors had. Leading in quantum could offer a similar, maybe even bigger, strategic and economic advantage across so many fields. Medicine, materials, finance, defense.
Governments are definitely noticing.
For sure. You see major funding from governments like DARPA in the US. And this idea of quantum computers working alongside classical ones in data centers hybrid computing that's gaining traction.
What's the next big milestone people are watching for?
A key target many are aiming for is getting to maybe 50 to 100 fully error-corrected logical qubits. That's seen as a point where you could start tackling some really significant, currently intractable problems.
Logical qubits meaning error-corrected ones, not just the raw physical one.
Exactly. You need many physical qubits, potentially thousands, to create one stable logical qubit. Reaching that 5100 logical qubit threshold would be a major inflection point.
So the vision is quantum computers starting in labs, then maybe specialized commercial uses, eventually becoming more integrated, driving jobs, shifting economies.
That's the trajectory many envision, yes. Starting as powerful tools for research, then filtering into industry, creating new capabilities, new markets, and yes, inevitably shifting the economic landscape.
So it really feels like we're right at the dawn of something potentially revolutionary. This isn't just faster computers, it's a different kind of computation.
That's absolutely the right way to think about it. It's a fundamental shift. These advancements, Zuchongzi 3.0, Majorana 1, they're signposts indicating we're entering a new era of computation with the potential to transform, well, almost everything, from industry to our basic understanding of the universe.
A profound transformation indeed. Lots to keep watching. Thanks for listening, everybody, and like and subscribe if you haven't already.